Chapter 2.5 has to do with Cartesian vectors, and what we want to do now is to express the vectors which is in 3D space in terms of its magnitude and direction angles. So in 2D space, it was very simple. If we had a force vector that lay in a plane, xy, and it was directed that way, we would know its magnitude, which would be the length of this vector, and the direction of it, we just needed to specify one angle. We didn't need to specify this angle because that's just simply 90 minus theta, and that's common knowledge, so we don't need to specify that. So in 2D space, all we need to do is specify magnitude and one angle. In 3D space, it's a little different. So in 3D space, because there are three axes, x, y, and z, and suppose we have a force vector F, we now need to specify its magnitude, which is just the length of the vector. Right, so it's just the length of this particular vector. But because it has x, y, and z, we actually need to specify three angles. We need to know what the angle that force vector makes with the x-axis, the y-axis, as well as the z-axis. So how do we go about specifying the direction of this force vector? We need to use some angles, and I'm going to demonstrate that by using this prop here. So I have this force vector F. It starts from the origin and it goes to this top corner, and I've labeled it as point A, and that force vector makes a certain angle with the x-axis, with the z-axis, and the y-axis. Furthermore, we can get even a better idea of how that force vector lines up with each of the plane is by looking at this model. So here I have the force vector, similar to before, and it goes to point O, and it gets directed to my point A. And we can see that it makes an angle with the x-axis, and in this corner right here it actually is a 90-degree angle. So I can take that out, and that is the plane that the force vector lies on right here. Right? So it'd be equivalent to something like that. So with that demonstration, then now we can go to a generalized picture such as this. We know that this is 90 degrees. I just showed that to you in my model there. And then we can go on to, so now what we can do is determine the angle that the force vector F makes with the y-axis, and we'll call that beta, and again this is 90 degrees. And finally, the angle that the force vector F makes with the z-axis is called gamma, right? That's called gamma, and again it's 90 degrees here. So to describe a force in 3D space, we need to specify the angles alpha. We need to specify this angle beta, and this is angle gamma, and we need to specify this angle beta. By specifying those three angles and the magnitude of that force, we have expressed the vector in 3D space in terms of the magnitude and the direction. Okay, so the last part of this section has to do with unit vectors. Unit vectors. So let's first define what a unit vector is. We know the magnitude of it, and it just is 1.0 and it's dimensionless as previously discussed. But what a unit vector is in relation to a given force is as follows. So I have my x, y, z coordinate system, and I have a force F in that direction. And what a unit vector is a vector along that direction of force with a magnitude of 1. So that is the unit vector for that force. So we'll call it the unit vector for force F. So how do we define that unit vector? How do we find out what that vector is? And it's simply given by the formula as follows, that the unit vector of that force is given by F divided by the magnitude of F. Now your book, if you look in your book, they use an example force of force A. So they say it's the force vector A divided by the magnitude of A. But it doesn't matter. The numerator has a force vector. The denominator is the magnitude of that force vector. So we can express this as the x component of A divided by the magnitude of A, I, plus A sub y over the magnitude of A in the j component, and likewise for the k component. And this is equation 2-6. Another expression for the unit vector is cosine alpha I plus cosine beta j plus cosine gamma k, and this is equation 2-7. Also, another thing is that we can take those cosine terms, square them, add them, and it should come up to always be 1.0. And this is equation 2-8. We can express a force vector in terms of the unit vector. So we can get the magnitude, so this is the magnitude of the force vector A, multiplied by the unit vector along that force A, and that would give us A cosine alpha I plus A cosine beta j plus A cosine gamma k. That can also be expressed as A sub xi plus A sub yj plus A sub zk. Okay, that's a lot of equations. That's many equations, but you have to memorize it. So how does one memorize it? Well, I would recommend making a note card like that and another one like that, and take it around with you wherever you go, and you should be able to memorize it fairly easily. Hey students, this is a bonus lecture. So we talk about this unit vector, and we say that the magnitude is 1. So let's see if that's the case. So let's say I'm given a force vector where the components are 4i plus 5j plus 6k newtons. And I can take the magnitude of that because I would be needing it. And that would be 4 squared plus 5 squared plus 6 squared. And that would come out to be 8.74 newtons. So we said that the unit vector is defined by each component x, y, z divided by the magnitude of that force vector. So let's write equation 2.6 for this force vector. Okay, so that means the unit vector for force F, or along force F, is given by force F divided by the magnitude, and that would be 4 divided by 8.74 I plus 5 divided by 8.74 plus 6 divided by 8.74. So if we compute each of these fractions, we get these values, and if it's truly a unit vector, I should be able to square each of these terms, sum them, and take the square root, and it should come out to be 1.0, meaning the magnitude of this unit vector is equal to the square root of 0.4558 squared plus 0.57208 squared plus 0.68 plus 0.68498 squared. I take the square root and it comes out to be 1.0. So yes, the unit vector has a magnitude of 1.0. I'm looking at the sheet and I have an error, and that error is in the notation. Unit vectors are dimensionless. I should not have newtons there, nor should I have newtons there. So that completes section 2.5.